Well, hello. I hope that you're all doing very well and are excited about learning some physics today. I'm your very own personal physics tutor, Dr. Rima McMullen, and you're very welcome to today's class on errors in measurements. You know that physics is a science subject, and what do we do in science? We do experiments, and in experiments we make measurements. Now we would like our measurements to be 100% accurate and precise, but unfortunately measurements are inherently infested with errors. All we can do is minimize errors in our experiments, but there is just no way to completely eliminate them. In today's class, we are going to talk about how many different kinds of errors are there, where they come from, and how they impact the results of our experiments. We're also going to look at how to calculate errors, and we'll go through several solved examples of finding errors in experiments. Alright, so let's begin our class. So we said that physics is a science subject. That means it is scientific. Now what do we mean by scientific? What does it mean for something to be scientific? For any theory, hypothesis, or statement to be scientific, it must satisfy the following two criteria. Firstly, it must be testable. That means you must be able to do experiments to either prove or disprove the theory, or the statement, or the hypothesis. Secondly, it must be replicable, meaning that if you perform several trials of the experiment, you must be able to get the same results. Let me ask you a question. Tell me if the following statement is scientific or not. A tree falls in a forest and makes a sound. There's nobody to hear the sound. There's nobody to see the tree falling, and there is no apparatus or instrument in the forest to make the observation of the tree falling and it making the sound. Did the tree really make the sound? Well, we don't know. Is this statement scientific? No. Why? Because can we test it? No, it cannot be tested. There was nobody to hear the sound. There was nobody to see the tree falling, and there was no apparatus, no instrument to make the observation, to record this event happening. Therefore, the statement that the tree, when it fell down in the forest, it made a sound. We don't know if it happened. We can't test it, and therefore it is not scientific. Experiment. What do we do in experiments? In experiments, we measured one or more physical quantities such as mass, temperature, time, electric current, potential, etc. Now these physical quantities, they are of three kinds: independent, dependent, and control. What's the difference between these three physical quantities? Also called as parameters or variables. Independent parameter or variable is the one that is being changed by the experimenter. This is changed by the experimenter. Dependent variable or parameter. It changes in response to change in the independent parameter. It changes in response to the change in independent. I'm going to write V dot for variable. And control is what is not changed. These parameters, these variables are kept fixed. So often when you're doing experiments, you will chart them, you will plot them. And the independent variable is plotted along the x-axis. Dependent is plotted along the y-axis. So we say that y, the dependent variable, it's a function of x. Let's understand this with the help of an example. Let's say we do an experiment to find out how the time period of a simple pendulum changes in response to the length of the pendulum. So this is a simple pendulum here. What is a simple pendulum? It's like grandfather's clock. Something that oscillates back and forth like this. And what is time period? Time period is the time it takes to go from one extreme to the other and come back. Or you can say that it's time that it takes to go from the equilibrium, from the middle position to the extreme, come back to the middle, go to the other extreme, and come back. The time taken to complete one cycle is its time period. So in this experiment, we are trying to see how the time period of a simple pendulum varies in response to change in the length L of the simple pendulum. Okay, so what I mean is that here, time period is the dependent variable, and length, we're changing the length of the simple pendulum. Maybe we start with 1 meter and then change it to 1.5 meters, and then we change the length to 2 meters, and so on till we get to 2.5 meters. And for each of these lengths, we are going to find out what the time period of the simple pendulum is. So since we are varying the length of the pendulum is the independent variable. Time period is measured in response to change in length. So time period may depend on the length. We don't know yet. We're doing this experiment to find it out. So we're going to say that time period is the dependent variable. And what are the controls? The angle theta, which is the angle of release of the pendulum, and the mass m, where mass m is the mass of the bob, the green colored bob. So we're not really going to get into the mathematical description of this experiment or the data associated with it. I just wanted to give you an idea of what dependent, independent, and control parameters mean in an experiment. So let's discuss an experiment. Let's say we're asked to measure the length of this rod. What kind of tool would you use to measure the length of the rod? I would use a ruler. This ruler is marked in centimeters. So the distance between these long lines, that represents 1 centimeter. But we also have these shorter lines. Distance between any two short lines, what does that equal? That equals 1 millimeter, which is called as the least count or the resolution of the tool or this device, which is a ruler. So the least count of any tool or device or instrument is the smallest measurement that can be made using that tool. So for this ruler over here, the distance between two short lines equals 1 millimeter. So the least count of this ruler is 1 millimeter, and another term for least count is resolution. Okay. All right. Moving on. To measure the length of this rod, what are you going to do? You're going to line up one end of this rod with the zero of the ruler and see wherever the other end falls. Okay. Now, this rod, it has the circular end over here. So it's not that easy to line it up with the zero of the ruler, is it? Not just that. The other end of the rod, it lies somewhere between 3.4 to 3.5 centimeters. We can't say for sure where exactly it lies. Maybe we can say that this is between 3.45 to 3.5. I mean, we can kind of guesstimate it, but still we can't say for sure if it's exactly 3.45 or 3.46 or 3.47, can we? There's just no way we could say that. So you can see it for yourself that using this ruler, all you can say for sure is that, hey, this ruler is somewhere between 3.4 to 3.5 centimeters long. How much it is exactly? We can't say it for sure. Is this your fault? Are you the one who doesn't know how to read a ruler? No, you're doing it right. I'm doing it right. It's the ruler. It's the limitation of the ruler. The ruler cannot tell us between 1 millimeter what the distance is, what the length is. That is the limitation of the tool that is being used. Any tool that you're using, it can't tell you for sure how much the quantity is if the quantity is less than its least count. It can't measure less than its least count. And the least count of the ruler is 1 millimeter. So now the length is between 3.4 to 3.5. It cannot tell you for sure. You can guesstimate it. You can make a very good guess, but you can't say for sure. So this is the reason why we say that every instrument has an inherent error in it, because no matter how precise your instrument is, it will still have some least count. And anything that's smaller than that least count cannot be measured very reliably using that tool. I hope that made sense. Let me know in the comment if it made sense or not. Okay, a recap. We said that in physics, which is a scientific subject, we do experiments. In experiments, we measure physical quantities, and every measurement has an inherent error. Cool? So far, so good? All right, moving on. Next, we are going to define a term called as absolute error. So what is absolute error? It is defined as the magnitude of true value minus the actual value. So you see these vertical lines? This means that I'm talking about the magnitude. I'm taking the absolute value. What does that mean? It means that, let's say, if the true value is 5 centimeters and the actual value is 7 centimeters, then this 5 minus 7, it is minus 2. But since we're taking the absolute value, we're taking just the magnitude, we're going to report this answer with the positive sign. That's what the magnitude or the absolute value or the modulus means. This is the formula for absolute error. It's the magnitude of the difference between true value and actual value. Now the question is, what is true value and what is actual value? Actual value refers to experimentally measured value. And true value is the theoretical value. This is what we expect. For example, if you perform an experiment to determine the value of acceleration due to gravity g on Earth, near the surface of Earth, we know that this value should be 9.81 meters per second square. So this is the theoretical value. This is the true value or the theoretical value. And in the experiment, let's say the actual value turns out to be 9.67 meters per second square. What would be the absolute error in the measurement of this g, which is 9.67 meters per second square, g experimental? You would write that as 9.81 minus 9.67. What does this give you? This will give you 0.14 meters per second square. So you see that absolute error has the same units as these quantities that you subtracted. I mean, you're subtracting two quantities. You cannot subtract oranges from apples. You can subtract only oranges from oranges. To be subtracted or added, each term must be same kind. Each term must have same kind of units. The next logical question to ask is, how do we get true value? We said that g on the surface of Earth is 9.81 meters per second square. But where does this value of 9.81 meters per second square come from? As a matter of fact, this true value that we're calling as theoretical value or known value is also an experimentally determined value. Take the value of any known physical constant, uppercase G, which is Newton's gravitational constant, speed of light, c, speed of sound in air, it could be Planck's constant. All of these that we say they are theoretically known constants. They have fixed values. Even they are experimentally found values. Next, we are going to introduce this symbol, delta. Delta represents change. So when we're talking about absolute error, and on the previous slide, we looked at absolute error for acceleration due to gravity. We had this value of 9.81 for true value, and we had 9.67 for the experimental value. On the left-hand side, the absolute error, it is an absolute error in the value of g. So we're going to write it as delta and g, because g is the quantity that is being measured. So this x that I have written here, this is like a generic symbol for physical quantity being measured. So if you were measuring, for instance, time, so here this is time true minus time experimental or measured, and on the left hand side you will have delta t. Here's a note about this delta t. Since this is the magnitude of the difference between the true value and the experimental value, this is always going to be positive. Okay, moving on. We're saying that delta x is x true minus x actual, where actual is the experimentally determined or measured value. All right, let's dive a little deeper into true value. We already said that all true values are measured values. True value is assumed to be the correct value of the physical quantity that is being measured. For instance, for acceleration due to gravity, it is 9.81 meters per second squared. For the speed of light in vacuum, it is 3 times 10 to the power 8 meters per second, and so on. So how do we calculate true values? So true value is found by calculating the average of several experiments. It is referred as x mean. X is the quantity being measured. X mean is equal to x bar. So whenever you put this bar over a physical quantity, this bar represents average. Average is also called as the mean. And we're going to call this as true value. So whenever the value of g was first established to be 9.81 meters per second square, some very precise experiments were performed, and whatever values of g they gave, I don't know, whatever, let's say they gave 10 values of g's, the average of these 10 values was taken, and it came out to be equal to 9.81 meters per second square. Okay? Now, this is not very common to write the average value as written between these pointy parentheses, but you might see it at some places. In quantum mechanics, this is called as expectation value of x, which is actually equal to the average value of x. So in terms of these symbols, you will say that delta x is equal to x bar, which is the average value of x over several experiments and is taken to be true value of x. And these values are usually known. You can find them in your textbooks. And if it is for a material that is bought from a factory, the factory will give you specification sheets. And they give you data sheets for the materials, and this number will be contained in those data sheets. And this x actual is your experimentally obtained value. Next, we are going to talk about relative error. Okay, so this relative error is measured with respect to something. It is also known as fractional error. So this is defined as absolute error, which is delta x divided by x true. You can also write this as delta x, the absolute error, divided by x bar. So it is absolute error over x true. For example, let's say you did an experiment, just like we said before, G experimental is 9.6 meters per second squared. Find out the relative error in this value of G. Will be G true minus G experimental absolute value divided by G true. So what do we get? 9.81 minus 9.67 absolute value divided by 9.81. This gives you 0.14 divided by 9.81, which is equal to 0.014271. Sure, we can't keep it going forever like the calculator is showing. Using the rules of significant figures, you're going to find out how many significant figures this answer will have. This should have two sig figs, so answer will be 0.014. Now, if you do not know how to find out the number of sig figs in this answer, I recommend that you watch one of my previous videos on significant figures. Alrighty. So, what are the units of this relative error? At the top, I have 0.14 meters per second squared. At the bottom, I have 9.81 meters per second squared. Dividing these two numbers will give me 0.014271. And dividing meters per second squared by meters per second squared, the units cancel out. So the relative error, which is also known as fractional error, is a dimensionless and a unitless quantity. It will just be a number. Make sense? Next, we're going to move on to relative or fractional percent error. So it's the same thing as the relative error times 100%. So here we found the relative error to be 0.014. To find out the percent error or the percent relative error or the percent fractional error in the same quantity, we're going to multiply this 0.014 by 100% and the answer will be 1.4%. So when you did this experiment to find the value of G and got the value of G to be 9.67 meters per second squared, and you're asked to find the relative or the fractional percent error in this experiment, your answer will be 1.4%. So this video lecture is devoted to a discussion of errors in measurements. And our goal in any experiment is to minimize errors. To do that, we want the individual values of x to be close to each other. So these individual values of x means whatever quantity we are measuring, we're calling that quantity as x. It could be whatever you're measuring. It could be time, it could be mass, it could be temperature. So whatever experiment it is that you're doing, ideally you should perform several trials of the same experiment. And when you perform several trials of the experiment, you're going to get several values of x, one from each experiment. So we're saying that we want these individual values of x to be close to each other. And the closer the individual values of x are to each other, that is, the smaller is the spread between individual values of x, the higher is the precision in the measurement of x. Now, the term precision has been defined before in one of my lectures in the same playlist. So if you haven't seen previous lectures in this playlist, I strongly recommend that you do watch those lectures as well. Let's discuss what precision means. Here's your target at the center, and you're given 4 darts to throw, and those are your 4 darts. These 4 darts, even though they're not on the target, actually they are nowhere near the target, but they're close to each other. So you say that your aim is quite precise. It's very precise. Why? Because each of these 4 darts, they have fallen very close to each other. The spread between these darts is very little. Therefore, your aim is very, very precise. Is it right though? Is it good though? That's a different story, but it's precise. So you will say that you have high precision. As compared to if you had thrown your darts as these green dots. This is your another trial. In this trial, your green darts land as shown in the picture. In this case, your precision is relatively lower. So your goal in any experiment is 1, to have high precision, and 2, you want your actual value to be close to it. You want it to be equal to the true value. Okay. So when the actual value is very close to the true value, ideally it should be equal to the true value, you will say you have high accuracy. Okay. Back to the same example. In the case where you have high precision, the darts, individual darts, they are far from the target, so your accuracy is low. And even in the case of green darts, if you take the average of these green darts, where do you think the average is going to lie? I say the average will be somewhere around here. Okay. And even this is quite long ways from the target, so you have low accuracy in both of these cases, 1 and 2. Let's look at another example. Same target. Let's say this time these are your darts. So what do you say about the precision of these darts? They're not very close to each other. Therefore, the precision is quite poor. The accuracy, on the other hand, I would say is quite good. Why? Because if you take the average of these 4 darts, it should actually be somewhere around here. Somewhere here. So the accuracy is good, but the precision is poor. Let's look at another example. In this third case, our darts end up at 9 o'clock, 12 o'clock, 3 o'clock, and 6 o'clock. What do you say about the precision? Again, quite poor. And how about the accuracy? Perfect, very high accuracy. I hope that these examples have helped you understand difference between precision and accuracy. Taking this further, here's your 4th example. All the 4 darts are at the center. Therefore, the precision is high. Why? Because these 4 darts are very close to each other. They are in very close proximity to each other. And since they are at the target, the accuracy is very high as well. High accuracy and high precision. Okay. And when you have high accuracy and high precision, your error is low. And this is exactly what you hope to get in an experiment. So you say that the closer the actual value to the true value, the higher would be the accuracy. And the smaller the spread in the individual measurements, the higher is the precision. Alright. So far we have discussed that in physics, which is a scientific subject, we're going to do experiments. In experiments, we are making measurements, and in every measurement, there is some error, no matter how careful the experimenter is. Then we looked at the definition of absolute error, relative error, fractional error, and relative percentage error. Then we talked about difference between precision and accuracy and claimed that we want high precision and high accuracy to have low error in an experiment. Next, we're going to talk about different kinds of errors in an experiment. Alrighty. So, in general, the errors are of 2 kinds, systematic errors and random errors. Systematic errors, as the name indicates, they will have some kind of system or pattern. They will display a consistent or proportional offset between the measured value and the true value. There can be several reasons for systematic errors. One of them is that your equipment is not calibrated properly. What does it mean? It means that, let's say, here's your mass measuring device. It's a scale here. Scale to measure mass. When you put nothing here, it should read 0. When you put 10 grams here, it should read 10 grams. When you put 20 grams on it here, it should read 20 grams, and so on. But what if when you put 10 grams on it, it reads 11 grams? And when you put 20 grams on this, it reads 22 grams. When you put 30 grams on this, it reads 33 grams. So this scale is not calibrated correctly. 1, 2, 3, 4. 10, 20, 30, 40, and this is in grams here. And this is just the experiment number. So first time you put 10 grams, it should be here. When you put 20 grams, it should be here. When you put 30 grams, it should be here. 40 grams, it should be here. This is what you expect. But what it does is instead, it gives you something like this. Does it make sense? So there's a proportional offset between these two lines. Maybe your equipment is faulty. It could be manufactured faulty, or maybe with prolonged use, or it's old. It can start giving wrong results, but the results will always be offset from the true value by a consistent amount. Or maybe you're using equipment improperly, or improper protocol, or wrong math. All these cases will lead to consistent or proportional offset between the measured value and the true value, and such errors are called as systematic errors. Luckily, if you could figure out the source of systematic error, it's very easy to get rid of them. All you need to do is just, get rid of the issue that's causing that systematic error. In addition to these, you may also have zero error of the instrument. That means maybe you're using a ruler and it's supposed to start at 0, but the 0 is broken off and it's starting at 1 millimeter instead. So all of your readings will be off by 1 millimeter in this case. Whatever you're measuring, it will consistently measure 1 millimeter longer than it should have measured in case this 0 had been there. Moving on to random errors. As the name says, they're random. They come due to unknown and unpredictable causes. And since we do not know their cause, how do we eliminate it? Random errors are very, very hard to eliminate. Why? Because we do not know their source. And random errors can come from misreading or fluctuations. Okay? Another look at difference between systematic and random errors. Let's say you have this, whatever, y-axis, x-axis, and you make some measurements for true values. All these measurements should lie on this straight line. Okay? But in your experiment, they lie over here on this yellow line, and between the blue line and the true value. So between the blue line, which is for the true value, and the yellow line for the measured values, there's this constant offset. There's this y offset. So this is a systematic error because all of the measured values, they're all pushed off to one side. There's a pattern in all of the measured values in the way that they're pushed away from the true values. Additionally, you could have a pink line like this. Even here, all of the measured values, they lie on this straight line. And this straight line is offset from the true value by a certain amount, in a certain fashion. So this is a proportional offset between true value and the measured values. Such errors are called as systematic errors. While in case of this diagram, where this should have been the true value, in the second diagram, this blue line represents the true value. That means in case there were no errors, then all of the measured values should lie along this blue line. This is where the true values lie. But since this is not an ideal experiment and we do have errors, when you do the experiment, this is your data set, all these dots. So you can see that these data points are randomly distributed about the blue line. There is no set pattern to these yellow dots. These are due to random errors. These are scattered in this totally unpredictable random fashion due to random errors. So this data set, it has high random error as compared to if I had my data set like this. Even now there is error. These dots are not on the blue line either, but they are very close to the blue line. So these pink dots, which represent my second data set, they have low random error. Low random error, high random error. And in the first diagram, we have systematic error owing to this constant offset or proportional offset. I hope that these visual representations make it easier to grasp the difference between systematic error and random error. Talking about visual representations, here's another one. We have seen these kind of examples before. All the dots, all my darts are at the target. Precision is good. Accuracy is good. Not much error. However, if I had my darts as shown in the second diagram, now these darts are relatively farther from each other. So precision is not very good. Accuracy is good because the average of these four darts will be at the center. So these are random errors. While in this third case, where all of these four darts are together, these darts have now systematically moved away from the target. There is a pattern in which these dots have moved away from the target. So in this case, there's an offset. There's a consistent, constant offset between each of these dots and the target, and therefore we have a systematic error here. Precision is good, accuracy is bad. So in case of systematic error, the data set has shifted away from the true values in a constant manner, in a fixed manner. There is a constant offset between the true value and the measured values. Since these data points are close to each other, we say that there is high precision. But since there is an offset between the measured values and the true value, the accuracy is low. In case of random error, these data points are randomly spread, randomly scattered about the true value. So the precision is going to be low. However, if we have sufficiently high number of data points, then the error in those data points will be such that when you take the average of those data points, the errors will cancel out. Make sense? Maybe not so much yet? Let's look at an example to make sense of it. Back to the example of measurement of acceleration due to gravity near the surface of Earth. Let's say we perform 10 trials of the experiment. Let's say these are our 10 experimentally determined values of G. While we know that the theoretical or the true value of G should be 9.81 meters per second squared. So individually, when we look at this data, it is spread on either side, on each side of 9.81. So to get the experimental value, we find out G bar, experimental. This is the average value of the experimental G. This is going to be 9.72 plus 9.78 plus 9.83 plus 9.89 plus 10.03 plus 9.80 plus 9.84 plus 9.61 plus 9.85 plus 9.79 divided by 10. What does this give us? That gives me 98.14 divided by 10 meters per second square, which is 9.814 meters per second square, rounded off to 3 sig figs because the theoretical value has 3 sig figs, so we get 9.81 meters per second square. So we see in this example that the individual values, they are randomly distributed about this theoretical value of G, which is 9.81. However, when we take the average, the individual errors of these values of G, they cancel each other out, and the average is fairly close. In fact, it's identical to the true value of G. So in case of the systematic errors and random errors, systematic errors are easy to get rid of. You need to identify them. Once you identify them, you can get rid of them. Either through your equipments, you can fix your equipment, or you can compensate for them in your calculations. Random errors, on the other hand, they are not easy to get rid of. You don't know what their source is. And when you make the sufficiently large number of measurements, since the data is randomly distributed, you will have some values that will be on the positive side, they will be higher than the expected true value, and some values will be lower than the expected true value. So when you take the average of all those randomly distributed values, the average will be close to the true value, and the bigger the set is for which you're finding out the average, the more accurate your value would be.